Something is already moving through our solar system right now, and the vast majority of people on this planet have absolutely no idea it is happening. There is a comet called C/2026 A1 MAPS, and it is heading directly into the most extreme environment any object in our solar system can enter. Not in 10 years, not in a decade, in a matter of weeks. And on April 4th, everything about this journey comes to a head. In the next few minutes, we are going to cover exactly where this comet is right now, and why observatories worldwide are tracking it every single night, what is actually going to happen on April 4th, and why those specific hours could be unlike anything most of us have seen in our lifetimes, why the most qualified scientist on the planet cannot tell you yet whether this comet survives or disappears completely, and the one thing you can do from your own home for free to witness this in real time. What makes this moment so rare is not just the comet, it is the window. You're watching this before April 4th. That means you still have time to understand what is coming before it happens. Most people scrolling right now will never get that chance. This comet has been falling toward the Sun for over 1600 years. The last time it passed anywhere near our part of the solar system, the Roman Empire was still one of the most powerful civilizations on Earth at that time. There were no telescopes, no tracking stations, no cameras in space. Nobody watching could have told you what they were looking at or when it would return. And now, in the spring of this year, that return is here. The final stretch of a 1600-year journey ends on April 4th, and the world is about to find out what happens when a comet this old passes this close to the Sun. Here is the first thing I want you to hold clearly. This is not a fear story. There is no danger to Earth, no impact, no threat. What this is, entirely and honestly, is a witness story. Something extraordinary is approaching one of the most extreme places in our solar system, and the window you have right now to understand it before it happens is narrowing. The scientists and astronomers who are watching this every night are not watching it because they are worried. They are watching because they are invested. There is a difference between those two things, and that difference is exactly what this video is about. Because on April 4th, one of two things is going to happen. Either this comet survives the most intense heat and gravitational stress our solar system produces and comes out the other side in a way that could be visible in our sky, or it does not survive at all. Or it breaks apart and fades, visible only briefly on the SOHO camera before disappearing entirely. Which outcome happens, nobody knows yet. The scientist watching its brightness curve every night cannot tell you. The observatories tracking its position across multiple continents cannot tell you. The physics can describe both scenarios with equal credibility. There is no math that currently settles this. Both outcomes are real, both are possible, and the genuine uncertainty in the fact that the answer has not been written yet is the single most compelling thing about this story. That kind of genuine uncertainty is rare in space news. Most events are confirmed before they reach a public audience. But you are watching this before April 4th. The story is live. And the fact that the outcome is still unknown is not a gap in the reporting. It is the actual state of the science. Here is what I know about the audience watching this. You have been following space news for a while. You have seen comet stories come and go. You remember when a previous comet was going to be spectacular, and it quietly fell apart before it ever delivered. You're not new to the setup and the disappointment cycle that sometimes follows. So I am not going to overpromise anything in this video. What I am going to do is walk you through exactly what we know, what we do not know, and why this specific event, April 4th, this specific comet, is drawing more coordinated scientific attention than most comparable events in recent years. And if you are new to this channel, welcome. This is a good video to arrive on, because what is coming is genuinely worth being present for. Before we go any further, hit that subscribe button, not as a routine click, but because April 4th is approaching fast, and when the cameras start picking up what happens near the Sun, you are going to want to be here for that follow-up. Drop a comment right now and tell me where in the world you're watching from. I want to know how many of you are going to be checking the sky, or the live camera feed, on April 4th, because wherever you are, what comes next is the kind of moment that does not come around twice in a lifetime. Let's start with where this comet is right now, because the journey it is already on is extraordinary, and the hardest part has not even begun yet. Right now, as you watch this, Comet C/2026 A1 MAPS is already deep inside the inner solar system. It has already passed through the orbital region of Mars. It has moved through the zone where Venus travels around the Sun, and it is getting brighter with each passing night. That brightening matters more than it might seem at first. As a comet falls closer to the Sun, the frozen material inside its core begins responding to the increasing warmth. Gases release, dust lifts off the surface. The material surrounding the solid core starts glowing as sunlight hits it, creating the broad, hazy halo that surrounds the nucleus. Scientists watch that glow intensify over time, and what they are seeing right now is a comet that is reacting to its environment in exactly the pattern you would want to see from something heading into a close solar encounter. It is active, it is venting, and that activity is what gives it a meaningful chance at what is coming. This does not mean survival is guaranteed. It means the comet is behaving like a healthy, structurally intact object so far. The difference matters. A comet that is already fragmenting or weakening on the way in tends to show brightness patterns that are unstable. Sudden jumps, unpredictable fading. What scientists are currently seeing is a consistent brightening curve, steady, on pace, not surprising the instruments in ways that would raise concern, and not yet producing the kind of explosive outburst that would have the entire community celebrating early either. It is holding right in the middle of what is possible, which means this question is genuinely still open. Observatories across multiple continents have now turned their attention to this comet, and the coordination between teams is already happening at a level you would typically only see for major solar events. Not because there is any danger, there is none, but because the scientific value of what this comet carries is real, and the opportunity to study it at close solar approach does not come around on a predictable schedule. When something this rare is doing something this consequential, you point your instruments at it and you pay attention. Here is what the tracking is actually showing in terms of trajectory. The comet is moving toward a solar distance that puts it significantly closer to the Sun than the innermost planet in our solar system travels during its own orbit, significantly. At the point of closest approach, it will be in a region where no instrument built by human hands could survive for long without specialized thermal protection. The comet has none of that. It has the frozen and rocky structure it arrived with, and whatever internal strength it has developed across the vast span of time it has been traveling. Some comets handle this kind of approach. Not most, but some. The ones that do tend to share certain characteristics. A core that is large and solid enough to hold together even as the outer surface burns away quickly, and a composition rich enough in certain materials to outgas heavily without triggering the kind of internal pressure events that can crack a nucleus from inside. Whether this comet has those characteristics is not yet confirmed. The instruments are watching the approach for any signs that go either direction. What makes the scientific community's attention particularly focused here is the comet's history. This object has not been in the inner solar system since the time of ancient empires. When it last passed through this region of space, the Sun looked the same, but the world watching it looked nothing like today. No spectrometers, no space cameras, no real-time data feeds, just a bright object crossing the sky that observers would have seen with their eyes, if it was bright enough, which may or may not have been the case on that ancient pass. What that orbital history tells scientists is that this comet has made very few close approaches to the Sun over its entire existence. Every time a comet passes through the inner solar system, it loses material. The outer layers heat, vent, and stream away behind it as a tail. A comet that makes this journey repeatedly over short periods gradually gets stripped down. Its volatile content depletes. Its internal activity becomes less dramatic with each pass. But a comet on a 1600-year orbit has not done this repeatedly. Its outer layers are not depleted. Its interior ices are essentially untouched by sunlight. The material that will be exposed as it approaches the Sun on April 4th may not have been touched by direct solar heat since the early days of the solar system. That is a meaningful scientific statement. It is not hyperbole. It is a consequence of the comet's orbital history and the physics of how comets change, or fail to change, over long intervals between solar passes. That preserved interior is one of the reasons scientists are coordinating their instruments so carefully. The gases this comet releases as it heats near perihelion are a direct chemical signal from the early solar system. You cannot recreate that in a laboratory. You cannot retrieve it from anywhere else. The only way to access that information is to be watching when the comet heats up, which is exactly what is happening right now and what will accelerate dramatically as April 4th approaches. In the days leading up to perihelion, skywatchers with good equipment and dark locations will be tracking the comet visually, watching it move against the background stars watching the tail develop and extend as the solar wind pushes the released material away from the nucleus. As it gets closer to the Sun, it will eventually become too close to observe directly. The solar glare will swallow it. It will disappear from view as seen from the ground, and that disappearance from direct view is where the story gets genuinely tense. Because before this comet reappears on the other side of the Sun, there is a period where nothing on Earth can track it. No telescope, no observatory, no ground-based instrument of any kind. The only camera that can see what happens is one that was placed in space specifically for this kind of moment, positioned to watch the solar environment when everything else goes dark. That camera becomes the most important tool in this entire story during the hours around April 4th. But before we get to the camera, let's talk about what April 4th itself actually looks like. Because what happens in those specific hours is the centerpiece of this entire journey, and once you understand the sequence of events in detail, everything else falls into sharper focus. April 4th is when everything builds to its peak. By the time that morning arrives, this comet will have been in freefall toward the Sun for weeks, accelerating every single day. As the comet gets closer, gravity pulls it faster and faster, and by April 4th, the comet is moving at a pace that makes almost any human comparison feel inadequate. It is not drifting toward its closest point, it is racing toward it, covering vast distances in hours that any spacecraft we have ever launched would require days or weeks to cross. Speed, in this case, cuts both ways. The faster the comet moves through the most intense zone near the Sun, the less time it spends being battered by the extreme conditions there. That is the protective side. But speed also means the transformative events. The heat, the outgassing, the structural stresses happen faster and more abruptly than they would at slower velocity. There is no easing into it. It moves through the most intense region near the Sun quickly, and everything that determines whether it survives or collapses happens within a compressed and unforgiving window. The environment the comet is entering near its closest solar approach is unlike anything in the human experience of heat or radiation. The surface of the Sun is extraordinarily hot by any standard we can reference. But the comet is not merely brushing by a hot surface. It is moving through a region of the solar atmosphere where the interplay of heat, radiation pressure, and charged particle bombardment reaches levels that stress the very bonds holding solid material together. The solar wind at this range is not a gentle breeze. It is a stream of energetic particles intense enough to blast surface material off the comet at tremendous rates, and the gravitational field at this proximity to the Sun is strong enough to act as a tidal force, essentially pulling on different parts of the comet's nucleus with slightly different strengths, because the near side is measurably closer to the Sun than the far side, and that difference matters at these distances. Heat, radiation pressure, charged particle bombardment, tidal stress, all of it at maximum intensity, all of it at the same time. If the comet's nucleus is large enough and structurally coherent enough, it can absorb all of that. The surface layers will strip away rapidly. Material frozen deep in the outer layers for a very long time will turn to gas almost instantly in that level of heat. But if the core is intact, if the deep interior is dense and strongly bound, it keeps moving. The stripping away of the surface is not destruction. It is transformation. And a comet that loses its outer layers but holds its interior together comes out the other side fundamentally changed but still present. If the nucleus is smaller than we hope, or if it carries structural weaknesses we cannot detect from the outside, the sequence is different. The tidal stress begins working on small internal fault lines. The outgassing from newly exposed material creates pressure from within the nucleus itself, pushing outward against the same structure the tidal forces are pulling apart. Those two forces working simultaneously on a nucleus that is already at its physical limits can cause it to fracture, and once the fracturing begins, it typically accelerates. What was one object becomes several, and then several becomes many, and the extreme heat and pressure complete the process. That is the threshold, and on April 4th the comet crosses it. Here is the specific sequence of events on April 4th, and one part of it is easy to overlook. As the comet makes its closest pass to the Sun, there is a period where it transits across the solar disk from certain lines of sight, moving between us and the face of the Sun in a geometric alignment that creates a natural trackable event sequence. That transit is brief, and it is exact, and it anchors the timeline of April 4th in a way that makes the whole day feel like it is built around a single point. But surrounding that transit is something more significant. Before the comet reaches its closest point, and during the approach through the peak danger zone, It enters a region where it is behind the Sun from Earth's perspective, hidden. Not just difficult to observe, completely invisible. The solar glare blocks it entirely from every ground-based instrument, and the duration of that hidden window, close to 2 hours, is where the entire story either turns or ends. During that window, the comet is at or extremely near the closest point of its entire 1600-year journey. The physics are at their most extreme. The stresses are at their peak, and from Earth, from every observatory, every telescope, every screen, there is nothing to see. The data feeds go quiet. The brightness readings stop updating. Scientists who have been watching this object every night for weeks are simply waiting. This comet has been travelling for over 1600 years to reach this moment. And the moment itself, the actual turning point of the entire journey, happens in a window of time where it is completely invisible to us. The most consequential stretch of time in this entire event is also the one where the least information is available, and the people watching know that. The scientists at their instruments know that. The observers with their cameras pointed at the solar limb know that. Everyone is watching a blank space where the comet used to be, waiting for it to come back, or not come back. When the comet re-enters the observable field of view after that hidden passage, the SOHO spacecraft cameras will be the first to pick it up. Not human eyes, not any ground instrument. A camera in space, positioned specifically to monitor the solar environment, will catch the first image of what just happened, and within seconds of that first frame appearing, scientists will have a strong initial read on the outcome. A clear, bright, well-defined object moving away from the Sun means survival. A diffuse, spreading smear without a defined central point means the comet has already begun to break apart. The signatures are distinct. The difference will not be ambiguous, but here is what I want to leave you sitting with before we move to the two possible outcomes. The comet itself is indifferent to all of this. It has no awareness of what it is moving through. It has no stake in the outcome. It is simply following the trajectory that physics has given it, responding to forces it has always responded to, carrying the frozen record of the early solar system in its interior with no concept of what that record means or what will happen to it. All of the meaning we give this event comes from us, from the people watching and paying attention. It lives in the people watching, in the data being collected, in the conversations being had about what this might mean for what we see in the sky on April 5th. The comet does not care about April 4th. We do. And that asymmetry, between the comet's indifference and our complete investment, is actually what makes this kind of event so resonant. The suspense, the deadline, the two possible endings, those are things we care about. The comet is simply following the laws of physics, and when the cameras come back online after that hidden window, when the first SOHO image updates, and we see whether there is a bright defined object moving outward, or a fading cloud spreading in all directions, that moment will answer a question that has been genuinely open for weeks. What does that answer look like? What does each outcome actually mean for the sky, for the science, and for everyone who has been paying attention? Let's lay both of them out clearly, because both are real and both deserve full consideration before April 4th arrives. The honest scientific answer to what happens on April 4th is that two outcomes are genuinely possible, and neither of them is just a theoretical edge case. Both are grounded in what we know about comets, about this type of solar approach, and about the specific characteristics of this comet as tracked so far. Scientists studying this object are not converging on one answer. They are holding both answers open because the data genuinely supports both. Understanding that is important before we walk through what each outcome looks like. Because the two-outcome structure of this story is not a dramatic framing device. It is the accurate description of where the science currently stands. Let's start with survival. If this comet clears perihelion intact, the first confirmation comes not from human eyes, but from the SOHO camera feed. A bright structured object, a defined nucleus trailing an extended tail, emerging from behind the solar limb on the outbound side. Scientists watching that feed will see the brightness level in those first frames and begin forming a picture immediately. A surviving comet will almost always be significantly brighter after perihelion than it was going in, because the sun strips away the outer surface layers during the approach, exposing the fresh interior material beneath. That fresh material, the ice and compounds that have likely not been heated since the solar system was young, begins outgassing aggressively when it is exposed. The rapid venting from a newly uncovered interior is what drives the brightness spike. And in the hours and days after perihelion, that brightness continues to evolve. What this means for what you can actually see depends on how much of the nucleus survived and how strongly it is outgassing in the days after closest approach. In the best-case scenario, and I want to be precise here that this is the most favourable possible outcome, not a prediction, this comet could reach brightness levels that make it visible without any optical aid. It could become something you look up and see in the sky with your own eyes, with a tail extending visibly away from the Sun in the days following April 4th. There is even a specific carefully framed possibility that at the moment of closest approach, during the day, a bright tail extending from near the Sun's position could be detectable by observers who know exactly where to look and are in a location with clear skies. Please understand the full weight of that framing. It is a possibility. It is the best-case scenario if the comet survives and brightens at the higher end of what scientists consider plausible. It is not a scheduled event. It is not a confirmed observation window. The history of comets that approach the Sun this closely is full of objects that looked like they should have produced something spectacular and instead emerged dimmer than expected. Still impressive to instruments, but not the kind of naked eye moment the projection suggested. The variables that determine peak brightness, how much of the nucleus survived, how freely the interior is now venting, how the tail geometry aligns with the viewing angle from Earth, are not things that can be confirmed in advance. They become known after the fact. What survival gives us, completely regardless of visibility questions, is something the scientific community genuinely cannot obtain any other way. The chemical data from a comet on a 1600-year orbit making its first modern-era solar approach is a one-time opportunity. The gas signatures captured by solar observatory instruments during and after perihelion will be analysed for years. That data informs how we understand comet formation, solar system chemistry, and the preserved record that long-period comets carry from the outer reaches of the solar system into the inner one. The scientific return from a surviving comet is enormous, and unlike visibility, which depends on factors that remain uncertain, the scientific return is meaningful at almost any brightness level. Now let's give the destruction scenario equal, honest consideration, because pretending it is unlikely serves nobody watching this. If the comet does not survive perihelion, the SOHO camera feed will show something noticeably different from a clean emerging nucleus. Rather than a defined bright object moving outward from the Sun, the feed will show a diffuse spreading of material, the comet's former nucleus now fragmented and dispersing outward in all directions under the influence of the solar wind. There will be no clear centre, no defined head, just a brightening fog spreading across the camera's field of view, growing less defined over the course of hours, and eventually fading entirely as the material disperses into the solar environment. This does not look like an explosion. It does not look violent in any observable sense. It looks, on the camera feed, like something becoming gradually less present. Within a day of perihelion, sometimes less, even that absence will no longer be distinguishable from the normal background noise of the solar environment. Even that absence will no longer be distinguishable from the normal background noise of the solar environment. For the scientists watching that outcome, the response is not failure. Every comet that does not survive its solar approach adds to the understanding of why some do and some do not. The data collected in the hours before fragmentation, the brightness curve, the spectroscopic signatures, the structural behaviour near perihelion, all becomes part of a growing dataset that helps future predictions. The end of the comet is not the end of its scientific contribution. It simply changes what that contribution looks like. But for those of us who have been paying attention, who have spent weeks following this story, learning about where this comet came from, understanding what April 4th means, the disappearance carries a weight that the scientific framing does not fully capture, something that has existed for longer than recorded human civilization, something that travelled an enormous distance across the outer solar system to arrive at this moment in the spring of this year simply stops existing. Quietly, without announcement. The sky on April 5th looks the same as the sky on April 3rd, and what was between those 2 days is gone. That deserves to be felt honestly, not dramatised, not amplified beyond what it actually is, but felt. Because the comet's disappearance, if that is the outcome, is a real event with real meaning, not a catastrophe, not a tragedy in any human sense, but a genuine ending to a genuinely long journey. Here is the piece of this that I think is most worth sitting with. Usually when something significant is about to happen, the outcome is already known before the audience is invited in. An eclipse has a confirmed path and a confirmed duration. A planetary alignment has a geometry that does not change. The math is settled before the event occurs. But this comet's outcome on April 4th is not settled in advance. It will be settled by physics, by the actual behaviour of actual material under actual extreme conditions. And the moment it becomes known equally for everyone watching. The scientists running the instruments are not ahead of you on this. They are waiting for the same first image you are waiting for, that shared moment of genuine discovery, where something unknown becomes known in real time and everyone sees it happen simultaneously, is extraordinarily rare in modern science communication, and it is available to you, completely and freely available, with nothing required except a willingness to be watching on April 4th. Which naturally leads to the question you may be forming right now. Why is this comet, specifically this one, specifically this approach, drawing the kind of sustained scientific attention it is receiving? Why are teams across multiple countries coordinating their instruments for this particular event? The answer to that question adds a layer of meaning to this story that changes how both possible outcomes feel. So let's go there before we talk about exactly how you watch this in real time. When scientists explain why this comet is drawing so much coordinated attention, they do not lead with its size or its speed. They lead with its age, and once you understand what that age actually means in a physical, chemical sense, not in a historical sense but in a scientific one, the significance of what is happening right now becomes much harder to set aside. This comet last passed through the inner solar system when the Roman Empire was still a governing political reality across much of the known world. The civilization that existed at that time had no way of knowing what they were looking at. If the comet was bright enough to see, and it may have been, observers would have watched it cross the sky over days or weeks and eventually disappear, with no framework for understanding its origin, its composition, or when it might return. It was simply a light in the sky that arrived, and then was gone. What those observers could not know is that the comet they were watching was carrying something that would still be there, completely unchanged 1600 years later. Because the interior of a comet, the deep core that sits beneath layers of ice and rocky material, does not change between solar passes unless it is directly heated. And this comet, on a 1600-year orbit, has not been heated significantly since that last pass. The frozen material in its interior has been sitting in the cold outer reaches of the solar system for all the centuries between then and now, unchanged, not degraded, not depleted, preserved. That preservation is what makes the comet's current approach scientifically irreplaceable. When the sun's heat strips away the outer layers of this comet during the approach to perihelion, what gets exposed is material that has not been touched by solar energy since the Roman era, or, in the deepest interior, possibly since the solar system formed. The gases released by that freshly exposed material carry a chemical signature that reflects the conditions that existed when those molecules were frozen in. Temperatures, pressures, all of it locked inside the gases the comet releases as it warms. Solar observatory instruments are positioned to read those signatures. Special light reading instruments that can identify exactly which gases a comet is releasing will be pointed at this comet during its perihelion passage. What they capture will tell scientists which compounds the comet carries in abundance, where in the early solar system it is likely to have formed, and how those materials compare to what has been measured in other long-period comets of similar origin. This matters to a larger scientific question that has been building for decades. The outer solar system, where comets like this one originate, is cold enough to preserve frozen gases that never survived in the inner solar system's early heat. Those preserved compounds are a kind of chemical record of what the solar system was made of before the inner planets formed in their current configuration. Every long-period comet that passes close enough to the Sun for detailed observation adds a data point to that record, and a comet on a 1600-year orbit adds a data point that is more pristine, more preserved, and more chemically intact than one from a shorter period comet that has been through the heating process many more times. There is also a structural question that scientists are watching for with specific interest. A comet that has not been close to the Sun in this longer period has interior ices that are essentially naive to the experience of intense solar heating. When a comet makes repeated short-period passes, its interior adapts over time. Certain frozen gases vent preferentially, the surface develops a crust that moderates the rate of outgassing, and the structural behavior near perihelion becomes more predictable. But a first-time or near-first-time solar approach, as this comet's 1600-year gap effectively represents, may produce outgassing behavior that is less controlled. The interior ice that was never close to the Sun does not know to be controlled about it. When the heat arrives, it responds in ways that a more experienced nucleus might have already moderated. Sudden pressure events from the interior, outbursts that are larger than the average outgassing rate would predict. These events are scientifically interesting because they tell you something about the comet's internal structure and volatile composition that a quieter, more predictable approach would not reveal. They are also, honestly, one of the factors that makes predicting the survival outcome so difficult. An outburst, a sudden brightness increase as fresh material vents rapidly, can be a sign of a healthy, volatile-rich interior releasing its contents under the increased solar heating. That is the positive reading. But a particularly intense outburst near perihelion can also signal that the nucleus is under significant internal stress and that the pressure being generated from within is working against the structural integrity of the core. The same event can be read two ways depending on other contextual data, and the instruments watching it in real time have to interpret quickly. This is part of why scientists across multiple countries are not just watching but actively comparing notes as the comet approaches. Data from one instrument alone gives a partial picture, but spectrometer data combined with brightness, curve data combined with SOHO structural imaging data, combined with ground-based positional tracking, gives something much closer to the full picture. And that full picture is what allows the most accurate possible assessment of what is happening inside the nucleus during the most critical hours. This is the specific, targeted focus of multiple research teams who have looked at what this comet is, where it came from, what it is carrying, and what the opportunity of this approach actually represents, and concluded that it warrants serious, coordinated effort. That is a meaningful signal about the scientific significance of what is happening. And all of it is accessible to you, not the spectrometer data that requires interpretation and will take time to process fully. But the direct observational experience of watching this comet approach and pass through perihelion is something that requires no specialized knowledge and no equipment beyond an internet connection. The camera that makes that possible has been running continuously for years, positioned specifically to watch exactly this kind of solar approach, and the feed it produces is publicly available in real time. Let me walk you through exactly what that looks like, how to find it, what you will see when you get there, and what the timeline looks like in the days leading up to and following April 4th. Because this is the part of the video that turns everything we have discussed from something you understand into something you can actually participate in. Everything we have covered up to this point has been building toward one practical, empowering conclusion. You can watch this happen yourself. The actual event as it occurs on a live camera feed, from wherever you are in the world, from your home, without any equipment, and without paying anything. The spacecraft that makes this possible is called SOHO, the Solar and Heliospheric Observatory. It is a joint mission operated by NASA and the European Space Agency, and it has been positioned between the Earth and the Sun for decades, watching the solar environment continuously without interruption. Its job, broadly speaking, is to monitor what happens near the Sun and transmit that data back to Earth, and one of the instruments it carries, a camera system called LASCO, is specifically designed to observe the region around the Sun in a way that ground-based observatories cannot match. LASCO works by using what is called a coronagraph. The principle is straightforward. The direct light from the Sun's disk is so bright that it overwhelms everything near it when observed conventionally. The same reason you cannot look directly at the Sun and see any detail in the surrounding sky. A coronagraph mechanically blocks the direct solar disk, creating an artificial eclipse that allows the camera to detect faint sources in the surrounding region. Coronal structure, solar wind outflows, and relevantly any bright object moving through the zone around the Sun. Comets making a close solar approach become bright enough to show up clearly on the LASCO feed. The combination of their large active coma and extended tail, both made luminous by the proximity to the Sun, produces a source that stands out distinctly against the darker background of the surrounding space. When a comet of this trajectory enters the LASCO camera's field of view, it appears as a bright moving streak, progressing visibly across the frame from update to update, with a tail pointing away from the Sun and growing longer as the comet gets closer to its closest approach. At the center is the coronagraph's occulting disk, a circular block representing where the sun's direct light has been removed. The edges of that disk sometimes show the faint glow of the solar corona. Against the dark background of the surrounding space, you can occasionally see stars moving slowly as SOHO's orientation shifts. When a comet enters the field, it appears as something distinctly different from a star, brighter, more diffuse, and visibly moving from one frame to the next in a way that stars do not. The tail makes it unmistakable. It is not subtle. Once you know what you're looking at, you will recognize it immediately. The SOHO website is publicly accessible. It is maintained by the mission team and does not require any registration, subscription, or account. A straightforward search for the SOHO LASCO C3 real-time images will get you directly to the right page. The C3 camera has the wider field of view, the one that will capture the comet's full approach and departure, and it updates its imagery on a regular cadence throughout the day. The images are time-stamped and arranged so that you can see how the scene has changed over the past several frames, which gives you the sense of motion even when you're checking in periodically rather than watching continuously. The comet's expected entry into the LASCO C3 field of view comes roughly 2 days before its closest solar approach on April 4th. At first, it will appear near the edge of the frame, faint, possibly just a point of light moving against the star background. As it gets closer to perihelion over those 2 days, it will brighten. The tail will develop and extend. The central coma will become more defined. By the time it is in the final hours before closest approach, it will be among the most prominent objects in the entire frame. And then it will reach the occulting disk. It will disappear behind the blocked region at the center of the image, and the frame will be quiet in that area for the duration of the hidden passage we talked about, close to 2 hours of the comet being completely behind the sun from the spacecraft's line of sight. During that window, the images will keep updating, but the area where the comet was will show nothing. That is the waiting period. That is the silence. When the comet re-enters the field on the other side of the occulting disk, moving now in the post-perihelion direction away from the sun, it will be the most significant image update of the entire event. The first frame showing what came out on the other side. This is the answer the whole story has been building toward. A clear, bright, structured object means the comet made it. A diffuse spreading cloud means it did not. You will be able to tell from the image what happened, within seconds of looking at it, without needing any specialized knowledge. The difference between a surviving comet and a fragmenting one on a LASCO image is not subtle. I want to say something about what this access actually means, because I think it is easy to take for granted. The SOHO spacecraft was launched decades ago, at a time when the internet barely existed in the form we know it now. The fact that its real-time imagery is freely and publicly available to anyone in the world who wants to see it represents a genuine commitment by the scientific institutions involved to the idea that scientific observation is a shared human activity. They built the camera, they launched the spacecraft, they positioned it between the Earth and the Sun, and then they made the images public. Previous generations did not have this. People who followed Halley's Comet in an earlier era had no access to real-time space imagery. They had newspaper reports and television summaries prepared hours or days after the observation was made. They received the story second-hand, already interpreted and packaged. You are receiving it first-hand. You're going to watch the same images the scientists are watching. At the same time, they are watching them, and form your own first impression of what you're seeing before anyone else has explained it to you. That is a genuinely different relationship to a space event than most people have ever experienced. It is participation, not just consumption, and for an event like this one, where the outcome is genuinely unknown in advance, that participation has real weight. Start watching the SOHO LASCO C3 feed around 2 days before April 4th. Watch the comet move across the frame, watch it brighten, watch it disappear behind the occulting disk, and then wait for it to come back, or not come back, on the other side. Set a reminder so you do not miss it, and consider telling someone else who would want to know. And whatever the cameras show when that first post-perihelion image updates, you will want to know what it means for the sky and for the science in the days that follow. Because the morning of April 5th is its own kind of moment, and understanding what comes next depends entirely on which of those two images you saw. When the morning of April 5th arrives, the question that has held this entire video together will have a confirmed answer. Not a probability estimate, not a projection. An actual documented result, captured in real time by instruments in space, visible on a camera feed that anyone can access, and known simultaneously to the scientists running the instruments and the people watching from home. The data from space cameras will give us a clear answer, and we will know. If the comet survived, April 5th will begin with something genuinely rare waiting in the sky. The comet will be moving away from the Sun at that point, gaining distance but still extraordinarily active from everything the perihelion passage triggered. The fresh interior material exposed by the closest approach will still be venting in the hours and days that follow, outgassing at a high rate, feeding a tail that continues to develop and extend. The days immediately after a successful perihelion passage are often when surviving sungrazers reach the most visually striking phase of their appearance. The nucleus is intact, the material venting from it is fresh and volatilaric, and the tail is at its most fully developed. If the comet survives, observers in the northern hemisphere may be able to see it low on the western horizon, after sunset or in the pre-dawn sky, in the days after April 4th. A comet with a visible tail, something discernible to the unaided eye from a dark enough location, or clearly trackable with ordinary binoculars from almost anywhere. If the brightness at perihelion was strong and the nucleus held its integrity well, the post-perihelion display could be genuinely impressive. I will say, as clearly as I said it earlier in this video, that is not a guarantee. The history of comets that approach this closely to the Sun includes plenty of objects that did everything right on the way in and still came out dimmer than expected, either because more of the nucleus was lost than anticipated, or because the outgassing after perihelion was less vigorous than the approach suggested it would be. A comet that survives perihelion is not automatically a spectacle. It is a survivor, and a survivor's subsequent behaviour depends on factors that only become clear after the fact. If it survived and you followed this video, you will know exactly where to look and what you're seeing, and that knowledge, that context, changes the experience of looking up. You're not a passive observer of a sky event. You're someone who followed this story from weeks before it happened, who understood the stakes, and who was watching when the cameras showed the outcome. The sky, after April 4th, will mean something different to you than it will to the person who only hears about it afterward from a headline. If the comet did not survive, if April 4th ended in fragmentation, and the SOHO cameras showed a diffuse cloud spreading silently away from the Sun, then the morning of April 5th has a different quality to it. There is no object to look for, no post-perihelion display to track, no developing story about how bright it might get over the coming days. What there is instead is a different kind of completion. A journey that began over 1600 years ago ended in the most extreme environment in our solar system. The comet that spent all of those centuries in the cold outer reaches of the solar system, carrying its frozen record of the early solar system intact for all that time, gave up that record near the Sun and then ceased to exist as a single object. The science that came from those final hours before fragmentation is not lost. The data collected by the instruments watching as it approached, the chemical signatures, the brightness behavior, the structural signals in the SOHO imagery, all of it remains and all of it will be analysed. Research papers will be written. The comet's contribution to the understanding of long-period sungrazers will be real and lasting. Its end is not the end of its meaning. But for those of us who were paying attention, who cared about this comet, who understood what April 4th meant, who watched the SOHO feed and held both outcomes genuinely open, the disappearance is still a loss worth acknowledging. Something specific passed through our solar system and is gone now. Something that had existed for longer than any human institution, that had been falling toward this moment for 16 centuries, reached the end of its journey. That deserves a moment of honest recognition, not because it is a tragedy in any human sense, but because it is real. Here is where I want to leave you, regardless of which morning April 5th turns out to be. The act of paying attention matters. Most of the people who share the sky with you on those mornings will not know any of this happened. They will look up at the same sky and see the same sky they always see, unaware that something remarkable just passed through the solar system. You are not in that group. You spent time learning about this. You understood the two possible outcomes before the event occurred. You watched with genuine investment in the result. That changes what the sky means when you look at it. Not the sky itself, but what you bring to the experience of looking. Space has a way, when we let it, of reminding us that the universe is far older and far larger and far more active than the daily circumstances of human life tend to suggest. And every so often something from that larger story passes close enough for ordinary people to notice, if they are paying attention. On April 4th, A 1600-year journey ends near the Sun. Whatever that ending looks like, you will have been part of the group that understood it in advance. If this story stayed with you, share it with someone who would want to know. Leave a comment. Tell me where you are watching from and which outcome you are hoping for. Subscribe so you are here when this channel covers what the cameras actually showed on April 4th. The follow-up is coming, the story does not close until perihelion does, and we will find out together.